In this video, we'll look at the accumulator pattern using the factorial function to demonstrate it. The factorial of a positive integer is defined as the product of the numbers from 1 to that number. 0 factorial is a special case and is defined as 1. The mathematical notation for the factorial is the exclamation point. 4 factorial is 4 times 3 times 2 times 1. We don't need to multiply by 1 since 1 is the identity element for multiplication. How would you write a program that allows the user to enter a non-negative integer and outputs the factorial of that number? What makes this different from the simple conversion problems we solved before is that the number of calculations depends on the value entered. In other words, the larger the number the user enters, the more multiplications we need to do. When you encounter a problem where the number of calculations varies, you should think about using a loop. Put one calculation in the loop, and then determine how many times the loop should run based on the number of calculations you need to perform. Let's calculate 5 factorial by hand. We'd start with 1 and multiply it by 2 to get 2, which is 2 factorial. Next we could multiply 2 times 3 to get 6, which is 3 factorial. Then we could multiply 6 times 4 to get 24, which is 4 factorial. Now we take that 24 result and multiply it times 5 to get 120, which is 5 factorial. How many multiplications did we do? 4, which is 1 fewer than the number we were calculating the factorial of. Now let's look at a Python version of the program. We'll start by getting the input. Next we'll write a loop that executes 1 fewer times than the number the user entered. Inside the loop we need to multiply the result so far by each number starting with 2. Since I will be 0 the first time through the loop, we use I plus 2 as the expression we want to multiply by. The next time through the loop, I will be 1, and we'll be multiplying by 3, so I plus 2 is the expression we want. We need to figure out what should go in place of the question marks. We need a value to build up, or accumulate, the final result as we saw when calculating 5 factorial by hand. So what we need to do is write factorial equals factorial times I plus 2. This is similar to how we updated the interest calculation in an earlier video. So if we write that as the body of our loop, it would crash the first time through the loop when we try to calculate factorial times I plus 2 because factorial does not have a value at the start. We need to initialize factorial before the for loop because we want to multiply 1 times 2 the first time through the loop. Factorial needs to be initialized to 1. So here's our final version of the factorial program. Note this also works correctly if the user enters 0. Factorial is set to 1, and the loop body never executes because range of -1 produces an empty sequence. If the user enters 1, the loop body never executes because range of 0 produces an empty sequence. But we set factorial to 1 before the loop, so it outputs the correct answer. Checking situations like these, known as edge cases, is important to make certain your code is correct. Now we'll look at the factorial program in PyCharm. Let's debug the program so we can see how it works. I'm going to set a breakpoint here on line 4 so it'll stop each time it gets there, and we'll enter 5 as our value. And now we can see the first time through the loop, factorial is 1, I is 0, and n is 5. So if we calculate I plus 2, we'll get 2, and we'll be multiplying 1 times 2 and updating factorial to be 2. Now the next time through the loop, I is 1, and so we're multiplying 2 times 3, and factorial will now be 6. And now I is 2, so we'll be multiplying 6 times 4 and getting 24. And now the next time through the loop when I is 3, we'll be multiplying 24 times 5 and getting 120. And now we see because 3 is the last value that's less than 4, that's the end of the loop, and now it will print out the result. Now we'll look at the general form of the accumulator pattern. Step 1 is to initialize the accumulator variable. Step 2 is to write a loop so that the number of times it executes matches the number of calculations we need to perform. And then step 3 is to write the body of the loop to perform 1 calculation and have it update the accumulator variable. This usually takes the form of the accumulator variable equals the accumulator variable, and then an operator and the amount to accumulate this time through the loop. We can see these steps in the factorial program. Factorial equals 1 is our initialization statement. The number of executions of the for loop corresponds to the number of multiplications we want to perform, and the body of the for loop updates the accumulator variable by performing 1 multiplication. Let's look at another example of the accumulator pattern to add up the specified number of odd values. First we get the input for how many numbers we want to add. because we were adding, we initialized the accumulator variable to 0, so 0 plus the first number results in the first number. Next, because we want to add that many odd numbers, the for loop runs n times. Inside the for loop, we add the next odd number. Since I will be 0 the first time through the loop, we use 2 times I plus 1, which is 1. The next time through the loop, I will be 1, and 2 times I plus 1 will be 3, which is the next number we want to add. You can see that this expression will go up by 2 each time since we're multiplying I by 2, and to make certain we have 1 the first time, we need to add 1. The range function is more flexible than we originally learned. We learned range of 5 would produce the sequence 0, 1, 2, 3, 4. You can send range 2 numbers, and it produces a sequence from the first number up to but not including the last number. Range of 2, 6 produces the sequence 2, 3, 4, 5. Note the difference between the two parameters tells you the number of values in the sequence. So for example, 6 minus 2 is 4, and 2, 3, 4, 5 is 4 numbers. You can send range 3 numbers, and the third number acts as a step value to indicate the increment for each number. So range of 2, 15, 3 produces 2, 5, 8, 11, 14, because we go up by 3 each time and stop before we get to 15. Notice as before, it does not get to the value specified by the second parameter. We still need to use list of range if we want to get an actual list. Now we can use the 2-parameter version of the range function to simplify our factorial example. We also initialize factorial to n, so we don't need to multiply by n in the last loop iteration. This allows our loop to execute 1 fewer times than the original version did. We need to multiply n by the values from 2 to n minus 1, so we use range of 2, n to get those values. And then each time through the loop, we just need to multiply by I.